2.6 goes over solving absolute value inequalities. When we are solving these absolute value inequalities, we are really dealing with compound inequalities. So with all of these inequalities, we are going to be turning them into two inequalities and solving both inequalities. You have to be very careful when you do these because sometimes you'll get something where you don't even have to solve the inequality because it'll already be starting with something that's a false statement or an always true statement. If it's starting off as a false statement, obviously your answer is no solution. And then if it's starting off with an always true statement, then we have infinitely many solutions, so all real numbers would be our answer then. If we look at example 1a, we're just going to focus on solving these today. So with these, we are given this absolute value of x plus 7 is less than or equal to 2. When we look at this, we see the absolute value of something is less than 2. Is that a possibility? Yes. So we can continue with this. We're going to turn this into two inequalities, getting rid of those absolute value bars because there is nothing on the same side with that absolute value right now. So this is going to turn into x plus 7. We're going to switch the sign. So it's greater than or equal to, switch the sign on the 2 to make it a negative 2, as well as x plus 7 is less than or equal to 2. From here, we just solve both inequalities. So on the one on the left, we're going to subtract the 7 from each side. We get x is greater than or equal to negative 9. For the one on the right, we subtract the 7 from each side, and we get that x is less than or equal to negative 5. When you compare these two inequalities, you want to see the one that has or includes the smaller number on the left-hand side. We have a negative 9 and a negative 5. The smaller number is on the left-hand side. So look at those inequality signs. They point in towards each other. So since they point in towards each other, this is an and statement. You'll rewrite this with your smallest number first, your variable in the middle, and your largest number last. You then just input your inequality signs open to the same term that it was originally open to. So with the x is greater than or equal to negative 9, it's open to x. It's going to stay open to x. With the x is less than or equal to negative 5, it's open to the negative 5. So it stays open to negative 5. So we have negative 9 is less than or equal to x, which is less than or equal to 5. For example B, we have the absolute value of 8x minus 11 is less than 0. The absolute value of any number is always positive. So is it possible for a positive number to be less than 0? No, it's not. So this is always going to be a false statement. So no absolute value will ever be less than 0. So this is no solution. For example C, we have the absolute value of x is less than or equal to 3.5. So look and see if this is a possibility. The absolute value of anything is a positive number. Is a positive number ever going to be less than or equal to 3.5? Yes. So turn this into two inequalities. We have x is greater than or equal to negative 3.5, as well as x is less than or equal to 3.5. There's no way to simplify these anymore because x is already by itself. So compare those inequality signs. The number that it occurs to the left is the smaller of the two numbers, so my inequalities are in the right position. Look at the signs now. Those signs point in towards each other, so this is an and statement. So we're going to rewrite this to where the negative 3.5 comes first, our x is in the middle, and then 3.5 is on the right. Those inequality signs are going to stay open to what they originally were open to. So between the negative 3.5 and the x, it stays open to x. And between the x and the 3.5, it stays open to 3.5. For example D, we have the absolute value of k minus 3 is less than negative 1. So again, ask yourself, the absolute value of anything is a positive number. Is a positive number ever going to be less than negative 1? No, it's not. So this is no solution. For E, we have the absolute value of 2w minus 1 is less than 11. Ask yourself, the absolute value of anything is always a positive number. Is a positive number able to be less than 11? Yes. So turn this into two inequalities. We're going to have 2w minus 1 is greater than negative 11, as well as 2w minus 1 is less than positive 11. And we're going to solve for both of these. I'm going to work with the one on the left first. I'm going to add that 1 to both sides. And I have 2w is less than negative 10. Then I just divide each side by that 2 and get w is less than negative 5. For the inequality on the right, I add the 1 to both sides. And I get 2w is less than 12. Then I divide each side by the 2. And get w is less than 6. Does my inequality on the left include the smaller of the two numbers? Yes. So I compare the signs. They point in towards each other. So since they point in towards each other, this is an and statement. So I'll rewrite it with my smallest number first, so the negative 5, then my variable, which is w, then my largest number to the right. From there, I keep my signs open to the original term that they're open to. So between the negative 5 and the w, my sign's open to w. And between w and 6, my sign's open to the 6. So we have negative 5 is less than w, which is less than 6. With our next example, example 2a, we have the absolute value of c minus 1 is greater than or equal to 5. So again, is the absolute value, so a positive number, capable of being greater than or equal to 5? Yes. So we're going to turn this into two inequalities. One that has the negative 5, one that has a positive 5. So we're going to get rid of those inequality bars, and we're going to have c minus 1 is less than or equal to negative 5, as well as c minus 1 is greater than or equal to 5. I'm going to work with the inequality on the left first. I'm going to add that 1 to both sides. I get c is less than or equal to negative 4. Now on the right, I add the 1 to both sides and get c is greater than or equal to 6. My smaller number is on the left with that inequality, so I compare the signs. They're pointed out away from each other, so this is an or statement. So I rewrite this towards c is less than or equal to negative 4, or c is greater than or equal to 6. For example B, we have the absolute value of k minus 3 is less than negative 1. So the absolute value of any number is a positive number. Is a positive number capable of being less than negative 1? No, it's not. So this one is no solution as well. For example C, we have the absolute value of 2w minus 1 is less than 11. So is a positive number capable of being less than 11? Yes. We're going to turn this into two inequalities. So we have 2w minus 1 is greater than negative 11, as well as 2w minus 1 is less than 11. We're going to add the 1 to both sides. We get 2w is greater than negative 10. Then we divide each side by the 2 and get that w is greater than negative 5. For the inequality on the right, I add the 1 to both sides. I have 2w is less than 12. And then I divide each side by that 2. And I get that w is less than 6. My inequality that includes a smaller number is on the left. I compare the two signs. They point in towards each other, so this is an and statement. So I'm going to rewrite this as -5 is less than W, which is less than 6. For example D, we have the absolute value of x plus 3 is greater than 8. So is it possible for a positive number to be greater than 8? Yes. We break this into two inequalities. So we're going to have x plus 3 is less than -8, and x plus 3 is greater than 8. We subtract the 3 from each side, and we have x is less than -11, as well as x is greater than 5. The inequality with my smaller number is on the left. My signs point away from each other, so this is an or statement. So I'm just going to rewrite it as x is less than -11, or x is greater than 5. For example, E, we have the absolute value of n plus 2 minus 3 is greater than or equal to -6. We're going to start this one by isolating the absolute value. So we just add the 3 to both sides, and we get the absolute value of n plus 2 is greater than or equal to -3. So with this one, the reason why we stop here is because you look at the absolute value. When you first looked at this, you had that -3 that was outside the absolute value bars, and this equation is this inequality does not have the absolute value isolated yet. You got to think with all of the other ones that we've done so far within this lesson, your absolute value has been isolated when you start. This one though is not. So you have to remove anything that's on the same side of those absolute value bars to the other side of the inequality to start with before you can even compare sides. So once you do that, you're left with this absolute value of n plus 2 is greater than or equal to -3. Now is when you can ask yourself, the absolute value of anything is a positive number. Is it possible for a positive number to be greater than or equal to -3? The answer is yes, always. So because the answer is always yes, the answer here is all real numbers. So you can write this double-backed R, capital R, to represent all real numbers for your answer. For example, F, we have 3 times the absolute value of D plus 1 minus 7 is greater than or equal to -1. So once again, we do not have the absolute value of something isolated, so we are going to remove the 3 and the -7 away from that absolute value in order to first isolate the absolute value of that D plus 1. You want to undo any addition or subtraction first, just like you're solving equations that have multiple steps. So we're first going to add this 7 to both sides. We have 3 times the absolute value of D plus 1 is greater than or equal to -1 plus 7, which is 6. From here, we would divide each side by that 3 and have the absolute value of D plus 1 is greater than or equal to 2. Now you can ask yourself, since the absolute value is isolated, the absolute value of any number is a positive number. Is it possible for a positive number to be greater than or equal to 2? Yes. So we're going to separate this into two inequalities. We have D plus 1 is less than or equal to -2, as well as D plus 1 is greater than or equal to 2. We subtract the 1 from each side and get that D is less than or equal to -3, as well as D is D is greater than or equal to 1. We compare those signs. Since our smaller number comes first and is on the left-hand side, those signs point away from each other, so this is an or statement. So we're going to have D is less than or equal to -3, or D is greater than or equal to 1.